In this video, we're going to work through what are called the Pythagorean identities. And I'll write them as we discover them, Pythagorean identities. I'm going to write them up here. There are actually 3 different Pythagorean identities. You really need to know one of them and have a working knowledge of it, and then you've got all of them. Okay. So it starts with just the equation of the unit circle. Okay. That's capital X squared plus capital Y squared is equal to 1. And remember, when we worked with circles, we derived that by saying that's just the Pythagorean theorem. Okay? Because if I look at this triangle that I have right here, this side is X, this side is Y, and that hypotenuse is a radius of the circle, so it's 1. Okay. So this really comes to us from the Pythagorean theorem. Okay. But now I can use the fact that the capital X and the capital Y value that I have here are cosine of theta and sine of theta. So this means that cosine of theta squared plus capital Y is sine of theta squared is equal to 1. And very often when we're squaring trig functions, we'll write it a little bit differently. Cosine squared theta plus sine squared theta is equal to 1. These 2 versions mean exactly the same thing. This is the more common way of writing it because we tend to get lazy and accidentally drop parentheses. If I were to write cosine of theta squared, that means I'm squaring the angle and then plugging into cosine. And that's not what I'm doing right here. I'm plugging into cosine and then squaring that result. Okay, so that's what these parentheses say. Don't square the angle, square cosine of the angle. Simpler way of writing that is if I put the square after the cosine, it says I'm squaring cosine. But of course, cosine only makes sense if it's cosine of something. So I take cosine of the angle and then I square it. Okay. You're welcome to write things either way. If you find it helpful to write things this way to remind yourself that that's what this means, it's totally fine, but make sure you know that that's what that notation means. All right, so this is the first of our Pythagorean identities, that cosine squared theta plus sine squared theta is equal to 1. Now, I said there are 3 versions of the Pythagorean identity, and if you have a working knowledge of this one, you have the other 2, because you can figure them out. If I start with cosine squared theta plus sine squared theta is equal to 1, and I say, that's dealing with cosines and sines. If I wanted something that involved tangents, I know from my quotient identity that tangent is sine over cosine. So tangent squared would be sine squared over cosine squared. If I take this equation and I divide both sides by cosine squared, now that would mean I'm dividing each term on both sides by cosine squared, because division, just like multiplication, would distribute over the addition. So all I did is say I want to have some cosines in the denominator. Since everything was squared, it made sense to divide through by cosine squared so that the power matched. And now I'm just going to simplify. Cosine squared over cosine squared is going to be 1. Of course, that's only true, of course, if cosine is not 0, but this whole thing is undefined if cosine is 0. Sine squared over cosine squared, notice that's just sine of theta over cosine theta quantity squared, because when you square a fraction, you would square the top and then square the bottom. And 1 over cosine squared, I can say that's 1 over cosine of theta quantity squared. Because, of course, if I square the top, which is 1, I'm just going to get 1, and then I would square the bottom to get the cosine squared. But then I can say, oh my goodness, sine theta over cosine theta, that's tangent of theta. So this is tangent squared theta. And the reciprocal of cosine, well, that's secant squared theta. So there's my next version of the Pythagorean identity. 1 plus tangent squared theta is equal to secant squared theta. Okay. Now, some of you are going to have that memorized. Some of you might not. And that's okay, as long as you remember the trick so that you know this one, okay, and then you know how to get to this one. You know that there is another version. And the version gives me a relationship between tan squared and secant squared, because tangent and secant have something in common. I can write both of them as a fraction with cosine in the denominator. So there's a Pythagorean identity that gives me a relationship between tangent squared and secant squared. And I find it by starting with my main Pythagorean identity and just dividing through by cosine squared. Now, there are two more trig functions that we have that haven't appeared yet. There's cosecant and cotangent. Well, they have something in common too, because they both have a sign in the denominator. So what I want you to do is pause the video. You're going to basically do this same work. You're going to start with this fundamental identity, cosine squared plus sine squared theta equals 1. Instead of dividing through by cosine squared, divide through by sine squared. And give me the third version of a Pythagorean identity. So go ahead and pause the video now and give that a shot. Okay, so following my own directions, I'm going to divide through by sine squared of theta. So I've chosen sine because that's what's in the denominator of cotangent and cosecant. And of course I've squared so that all of the powers are the second power. Cosine squared over sine squared, that's cosine theta over sine theta, quantity squared. But that's cotangent squared. Sine squared theta over sine squared theta is going to be 1, provided, of course, that it's defined so that sine of theta isn't 0. But if sine of theta were 0, all of these terms would be undefined. And this is the reciprocal of sine squared. So that's cosecant squared theta. So we've got cotangent squared theta plus 1 equals cosecant squared theta. Now, you need to be able to work with all three versions. You may or may not choose to memorize all three. It's pretty quick to get there by dividing through by the appropriate trig function squared. So for years, I didn't have these two memorized. I knew this one, and I would get these two by just going through this division. I've done it often enough that I've now accidentally memorized them, so I remember them without having to do that work. But I never sat down and said, I must memorize all three versions. I just figured them out so often that, oops, I memorized them. Okay. I want to just show you why these trig identities can be useful. Okay. Just an example. There are lots of reasons they can be useful. But if I have cosine squared theta plus sine squared theta equals 1. Notice I can rearrange this equation to say that cosine squared theta is 1 minus sine squared theta. Okay. Now, let's suppose I was asked to take the square root of 1 minus sine squared theta. That's not super convenient because square roots do not distribute over addition and subtraction. So I can't just take the square root of each term and subtract the results. That's just right out. Okay. But what I can do is say that's the same thing as the square root of cosine squared theta. So instead of having a subtraction problem involving two terms, I can just write it as one term. And then I know what the square root of cosine squared theta is. Take a moment. Be very careful. I'm guessing some of you are going to get this wrong. It's the absolute value of cosine of theta. Don't forget that absolute value, because the square root of something can never be negative. But I know that cosine of theta is often a negative value, so that absolute value is very, very important. Okay? But it allowed me to simplify it. So here, writing things this way made my expression easier to work with than when I had written things this way. And that's really what identities are going to do for us. They're going to give us some options that make things simpler in some cases.